IP addresses are 32-bit numbers, and they are represented as a binary value of 1 or 0. We group these into chunks of 8 bits, and then we convert those 8 bits to a decimal value, separating them with a dot or a decimal point so that they're easy to read. So in this example, we have a 32-bit binary number. That number is 10101100, 0001, 0000, 1000, 0000, 0001, 0001. Now, saying that address is not easy. Remembering that is even more difficult. So for readability, we'll take that 32-bit number and we'll divide it into 4 octets. Each octet is going to contain 8 bits. Once we've got it separated into octets, we can take that value and convert it into a decimal number. The way that we do that is by adding up each value that has a 1 with the corresponding place value. So the chart would look something like the following: 128, 64, 32, 16, 8, 4, 2, and 1. If we take that first octet, which has a value of 1, 0, 1, 0, 1, 1, 0, 0, and we add up the place value in each location where the binary value is set to 1, we would be adding 128 plus 32 plus 8 plus 4, and that value in turn would give us the decimal number of 172. If we were to do the same with the next octet, we'd get a value of 16. With the following octet, a value of 128, and with the last octet, a value of 17. So each octet has a decimal value. We separate that value with a decimal point, 172.16.128.17. A much easier number to remember. And a much easier number to communicate as opposed to a binary value. Once we have an IP addressing scheme, we allocate IP addresses to our devices. All of the devices that reside on the same network are going to have a portion of the address that is identical. In this example, the engineering subnet is 192.168.1. Each host device is going to have a unique value, and that's why we have host number 2, number 3, number 4, and our router, which is the equivalent of a host on that particular subnetwork, with a value of 1. On the opposite side of the router, we have the manufacturing subnetwork 3, which is on the 192.168.2 subnet. The router host address for that subnet is going to be .1, and then we're going to have .2, .3, and .4 respectively. Now each of these networks is going to have its own address, and that is the 0 address in the host field. So on the engineering subnet, if we were going to iterate the network address, it would be 192.168.1.0. On the manufacturing network, if we were going to iterate the network's address, it would be 192.168.2.0. But how can we tell the difference between the network ID and the host ID? To do so, we need to use an address mask. An address mask is another 32-bit number that we use as a decoder. When we stack it up against the IP address, any bit in the subnet mask that is turned on or set to 1 counts that corresponding address bit as network ID. In this example, we have an IP address that's represented in binary. Right underneath it, we have a subnet mask that is represented in binary. The very first octet in the subnet mask has all of the bits enabled, or turned on or set to 1. And so this would indicate that the first octet in the IP address is the network portion. All of the bits that are set to 0 in the subnet mask, those corresponding bits in the IP address, are host bits. Therefore, when we convert this binary value to decimal, the 10 portion of the IP address is the network ID, and the 7.4.5 portion of the decimal value of this address is the host side, or the host portion of the address. This would make the subnet mask 255.0.0.0. Because the first 8 bits are enabled, we would call this an 8-bit subnet mask, or a /8 prefix. If we were to enable the first 16 bits, it would be a /16, and if we were to enable the first 24 bits, it would be a /24. Again, the bits that are enabled are the bits that identify the network portion of the IP address.